In this chapter, we'll focus on reactions of alkyl halides and tosylates. I will use the designation X for halides and tosylates. Tosylate leaving group is a conjugate base of tosylic acid or para-toluene acid, and tosylate is an excellent leaving group, and we'll treat it as a pseudohalide. There are two types of chemical reactions that we'll cover in this chapter. First, we'll focus on the nature of substitution. In substitution, a nucleophile, which is also a Lewis base, will attack the carbon atom attached to the leaving group. The leaving group will be expelled, giving us substitution product. In the next tutorials, we'll talk about elimination, where the product is an alkene. Instead of nucleophile attacking the carbon atom attached to the leaving group, in those reactions, basic nucleophiles will instead abstract a proton, hydrogen ion, from the so-called alpha carbon. Alpha carbon is the carbon atom next door to the unit in question, in our case, alkyl halide or the R-X. Substitution follows the following pathway. In general, nucleophile, which can be either neutral or negatively charged, will attack the electrophilic carbon. The leaving group will be expelled, giving us the substitution product. We'll study the nature of the nucleophile and the leaving group in greater detail later on. But for now, let's just take a look at some potent nucleophiles such as thiolate, cyanide ion, and iodide. Notice that the nucleophilic character of this ion increases as you go down the periodic table. So for example, if we compare the reactivity of thiolate versus its oxygen analog hydroxide, notice that difference in the order of magnitude. So the larger the nucleophile, the less tightly held are the outermost electrons on the atom in question, and therefore they're more nucleophilic. As for the leaving group, best leaving groups are tosylate, iodide, and bromide, which are weaker conjugate bases relative to fluoride, chloride, and bromide. So if you think about the strength of the conjugate acids of fluoride ion versus iodide ion, think about HF, which is much stronger acid than hydriodic acid. The weaker the conjugate base, the better the leaving group. Substitution mechanisms follow two general pathways. SN1 mechanism, which stands for nucleophilic substitution, unimolecular. This mechanism follows the first order kinetics, where the general notation for the rate law or reaction rate will be expressed by rate is proportional to the constant K times the concentration of the alkyl halide or alkyl tosylate. And we'll talk about the kinetics a little bit more later on. So for this type of reaction, we have two steps, with the first step being the rate determining step, and it involves formation of the carbocation. This reaction is most favored for tertiary alkyl halides and also primary and secondary allylic and benzylic alkyl halides. So the generic mechanism involving, for example, tertiary alkyl halide will involve dissociation of the leaving group in the rate determining step, giving us the carbocation intermediate, followed by addition of nucleophile, which occurs more readily, to get the substitution product. Since formation of the carbocation is the rate determining step, therefore we can predict what types of alkyl halides and tosylates will be most favored for this type of chemical reaction. So if we think about the relative order of stability of carbocations, we know that methyl carbocations do not form in solution, they're unstable, and same goes for primary carbocations. However, some secondary and definitely tertiary alkyl halides undergo this reaction readily. So here's an example of tertiary alkyl halide. And the same goes for primary allylic alkyl halides, because the incipient carbocation will be stabilized by delocalization, and for benzylic carbocations next door to the benzene ring. So here's an example of primary benzylic alkyl halide. SN2 substitution, on the other hand, follows bimolecular second-order kinetics, so substitution, nucleophilic, bimolecular, and it proceeds via one step. There's no carbocation or any other intermediate that forms, but the initial transition state dissociates to give the product. And the rate law for the second-order kinetics will be proportionally constant times the concentration of both alkyl halide and the nucleophile. This reaction is subject to steric effects, and therefore it occurs most readily at primary and some secondary alkyl halides. So these reactions are favored for methyl halides, and primary alkyl halides. There are two stereochemical outcomes possible in substitution. So the two modes are inversion and retention. So if the initial alkyl halide has the stereogenic center at the reacting carbon, for example, here we have 4 different groups bonded to the carbon in question. Here's our leaving group X. And assuming that the group R1 has a higher priority than group R2, so we have priority assigned as 1, 2, and 3. So we have S absolute configuration of the stereogenic center. And here is a reaction with thiolate ion as the nucleophile. In inversion, mechanism, our absolute configuration at the stereogenic center will be inverted. So if you start with S enantiomer, you will end up with R and vice versa. So that's one possible mode which proceeds via Walden inversion, which is umbrella type of like inversion. The second possible outcome is retention of the absolute configuration at the stereogenic center. So again, starting with S configuration at the carbon in question, nucleophile thiolate displaces the leaving group bromide, and the absolute configuration is retained. As far as the kinetics of nucleophilic substitution, let's just review some of the concepts. Rate of the chemical reaction is simply change in concentration of the substrate with time. So if we take a look at some sample representative reaction when the substrate S is converted to product P, then we can write down the rate law V for this type of reaction as the change in concentration of the substrate with time. So if we substitute the concentration of reactants and conversion to product rate with the proportionality constant K, then our rate becomes simply K times the concentration of S. So kinetics has to do with observing the decrease in the concentration of the substrate and increase in the concentration of the product with time. And the units for the rate are typically molarity or concentration per time. So liter per mole times second from molarity. And the rate law is the outcome of the mechanism. So if we look at the notation for the rate law or expression for the rate law, we can predict we can discern what the mechanism is. So the order of a reaction is the sum of the components of the concentrations of the species participating in the rate determining step. For reactions such as this one, for example, where we replacing the leaving group bromide with a nucleophilic hydroxide, we can write down the expression for the rate law since we have a methyl bromide, which will not form a carbocation. So this will be SN2 type of reaction. So our rate will be proportionality constant times the concentration of the alkyl halide, in our case, methyl bromide, times the concentration of the nucleophile, in our case, base, sodium hydroxide. So second order kinetics. So let's focus on the first type of reaction mechanism, which is the SN2 reaction. This reaction proceeds with inversion of the reacting carbon atom. So if there is a stereogenic center, it will be inverted from R to S. It follows second order kinetics. So the rate depends on the concentration of both the nucleophile and the alkyl halide, as both of those species participate in the rate determining step. And the transition state, and again, there's no intermediate, the transition state is planar at the reacting carbon center. So if we take a look at the nucleophile that approaches the alkyl halide in question, so alkyl halide is tetrahedral at the reacting center, we have 1, 2, 3 groups, and we have a leaving group. So this is our leaving group. So as the nucleophile approaches from the backside, from anti-periplanar orientation relative to the leaving group, so as the nucleophile approaches, we have a transition state in which the incipient bond between the nucleophile and the carbon atom is not yet fully formed, and the bond to be broken, the sigma bond between carbon and the leaving group, is partially broken. So the carbon atom in a transition state has its 3 remaining groups, 1, 2, 3, in a trigonal planar arrangement. So essentially it is flat. It is planar at the carbon center. So as the nucleophile pushes in to form the bond and the leaving group breaks away, the 3 substituents are inverted, sort of like an umbrella in the wind, giving us inverted stereogenic center. So nucleophile is now bonded at the carbon in question, and the leaving group is fully dissociated. So no intermediate, just transition state, which then leads to formation of the product. So let's talk about different factors that affect the rate of the reaction and the propensity of alkyl halides to undergo such reaction. Let's talk first about the nature of the alkyl halide. So SN2 reaction, since you have 5 groups surrounding the reacting carbon center in a transition state, as you would expect, is very prone or liable to steric effects. If there is much steric hindrance at the reacting carbon atom, the reaction would not be favored. So not surprisingly, methyl halides and tosylates are most reactive. So if we have, for example, methyl iodide, or methyl tosylate, since hydrogen atoms are small, nucleophile readily approaches the carbon atom from the backside without much crowding at the carbon center to give the corresponding product. After methyl halides, primary alkyl halides and tosylates are next most reactive. And again, we have 2 small hydrogen atoms and some sort of R group, which again creates a good environment that it's not very sterically hindered for the nucleophile to approach. So the nucleophile follows the antiperiplanar trajectory of the attack, so from the backside as the leaving group breaks away. Secondary alkyl halide might react, especially those at the benzylic and allylic position. So the secondary alkyl halides are the gray area because they undergo competing processes such as elimination. And let's take a look at the secondary allylic alkyl halide. So there is more steric crowding, but allylic and benzylic and some aliphatic or alkyl halides will also undergo SN2 depending on other factors such as solvent, nucleophile, and the leaving group. Tertiary alkyl halides or tosylates do not undergo SN2 chemical reaction. So there is too much steric hindrance for nucleophile to approach a tertiary carbon atom. So we'll focus on the reaction of methyl, primary, and some secondary alkyl halide tosylates. And here is an illustration how the steric effects influence the rate of SN2 reaction. So in 4 cases here, we have reacting carbon center, which is this carbon atom here, and the leaving group is in red. So here's our leaving group X. And we successively increase the steric environment around the reacting center. So in this case, we have methyl bromide. So we have carbon center that's very accessible to the attack by the nucleophile. There isn't much steric hindrance, and not surprisingly, those are the compounds that undergo SN2 reaction most readily. Leaving group, although much larger than carbon atom or the hydrogen atoms, is on the other side, 180 degrees away from the trajectory by which nucleophile approaches. So the size of the leaving group in this context is not important. So we're looking at the steric environment on the other side of the leaving group right here. So let's see what happens when we increase the steric hindrance around the reacting carbon atom. Here we have a primary alkyl halide. So now nucleophile can still readily approach because on the backside of the reacting carbon, there is still not that much of steric crowding. We have a methyl group on the side and 2 hydrogen atoms. When we increase the coordination of the reacting carbon to secondary, so here we have secondary alkyl halide, notice that it's much more difficult for the nucleophile to get through in between the 2 carbon atoms. Here's carbon atom attached to the reacting carbon, and here's another one, and 1 hydrogen. So there is much crowding. And the tertiary alkyl halide simply does not have enough room for the nucleophile to attack from the backside. So tertiary alkyl halides and tosylate will not follow that mode of nucleophilic attack. So order of reactivity in SN2 reaction with respect to the nature of the substitution at the reacting center increases from tertiary, which do not react via this mode, all the way to methyl. So notice the difference in the order of magnitude. So primary methyl bromide followed by primary, followed by secondary. And then take a look at the specific case of a primary alkyl halide. So this is still primary alkyl halide because this carbon is connected to only one other carbon atom, is not reactive at all. So compare this primary alkyl halide, neopentyl bromide, with this primary alkyl halide. Notice the different order of magnitude in reactivity. Neopentyl will not react at all, even though bromide is attached to the primary carbon atom, because next to this primary carbon, we have a quaternary carbon atom, which crowds the backside of the reacting carbon to such extent that nucleophile cannot approach. So even though we have a primary carbon, since we have a quaternary carbon next door, there is just too much branching to allow for any nucleophile to approach from the back. Let's now take a look at the nucleophile. We can have either negatively charged nucleophile or a neutral nucleophile. So if we start with a negatively charged nucleophile, we end up with a neutral product. For example, if I have primary alkyl tosylate reacting with a cyanide ion, which is a potent nucleophile. So if I add the nucleophile in the form of sodium cyanide, then my nucleophile will attack the carbon from the backside. Tosylate will be expelled, giving me a nitrile product. So starting with negatively charged nucleophile, I end up with a neutral nitrile product. If the nucleophile is neutral, such as ammonia, NH3, or water, so let's again try tosylate, primary alkyl tosylate, and let's react it with a neutral nucleophile, which can, for example, be a co-solvent, or it can be ammonia. So if we have H2O as a nucleophile, and again, nucleophile will approach from the backside, tosylate will be expelled, then our initial adduct will need to be deprotonated. So when we start with a neutral nucleophile, the product is positively charged and it requires additional deprotonation step. So let's take a look at some nucleophiles. As you go down the periodic table, the size of the atom increases, and so does their nucleophilic character. So if you compare, for example, two analogs from group 6A chalcogens, hydroxide ion and hydrosulfide or thiolate ion. So thiol group, as you recall, is SH. So if we deprotonate, we have thiolate ion, SH minus. So SH has the same Lewis structure as OH minus. And notice since sulfur is larger and therefore the electrons in its outermost shell are less tightly held than those valence electrons in oxygen, those electrons are more available to the nucleophilic attack. So same applies to halide series. Iodide is more nucleophilic than bromide, which in turn will be more nucleophilic than chloride. So as you're comparing nucleophiles that are in the same column on the periodic table, as you go down, their nucleophilic character increases. And weakest nucleophile are neutral, obviously, so the more the negatively charged species are more reactive. Let's take a look at the leaving group. The leaving group, if it's a weak base that can subsequently disperse or delocalize its negative charge across the framework of the ion, are better leaving groups than those that are small and hold their electrons tight, such as fluoride or chloride. So the worst leaving group are strong bases such as amide ion, alkoxide ion, hydroxide, and fluoride. So these leaving groups, or those groups, are not leaving groups, not good leaving groups. So we really want to focus on these three leaving groups: tosylate, iodide, and bromide. In order for hydroxide or amide or alkoxide to be expelled, we would need to activate them first, using, for example, PBr3 or thionyl chloride. So the leaving group, as it's expelled, it's negatively charged. So leaving group will be negatively charged, and therefore the weaker the base, the weaker the conjugate base of the acid, the better the leaving group. And the leaving group also, since in a transition state, it is still associated with the carbon, with the reacting center, has to be able to stabilize and delocalize the charge imparted by the nucleophile. So any group such as iodide or tosylate that can disperse the negative charge will also stabilize the transition state. So best leaving groups again will be tosylate, iodide, and bromide. And again, take a look at the difference in order of reactivity. Tosylate is 60,000 more times more reactive as a leaving group relative to fluoride, which is a very strong base of the weak conjugate acid, hydrofluoric acid, and therefore less likely to be expelled and exist as an ion in solution. So poor leaving groups that would first need to be activated in order to be expelled are fluoride, hydroxide, alkoxide, and amide. So these compounds would not undergo SN2, direct SN2 reactions. Solvent. Solvent is really important in SN2 reaction, And solvents that are protic, meaning those solvents that can form hydrogen bonds, so those compounds that have nitrogen-hydrogen bond or oxygen-hydrogen or sulfur-hydrogen, these will slow down SN2 reactions because they will associate themselves with reactants via hydrogen bonds. So therefore, best solvents for SN2 reaction are aprotic solvents, solvents that do not have hydrogen bonds that can be donated or associated with the reactant. But solvents that best promote SN2 reaction need to be polar. So we want to have a solvent with a high dielectric constant. So that would be a solvent that will have a lot of dipole interactions resultant from the dipole moments between electronegative and non-electronegative atoms. Those solvents are HMPA, hexamethylphosphoramide. So if we take a look at the structure of hexamethylphosphoramide, we have phosphorus with a carbonyl and with nitrogen with two methyl groups. So hexamethyl because we have 6 methyl groups. Phosphoramide because we have the phosphorus analog of the amide. And we have so many dipole moments here. We have a dipole moment between each carbon atom and nitrogen, dipole moment pointing toward nitrogen, and also 3 dipole moments between phosphorus and more electronegative nitrogen atom. So it's a very polar solvent with high dielectric constant, but with no hydrogen bonds. Notice that there are no hydrogen atoms bonded to electronegative atoms. So hexamethylphosphoramide is the most potent solvent that best promotes SN2 reaction, followed by acetonitriol, followed by DMF or dimethylformamide, and again we have dipole moments between nitrogen, carbon and nitrogen, resulting in high polarity or high dielectric constant. So many dipole moments and no hydrogen bonds. And finally, dimethyl sulfoxide, which has a dipole moment between carbon and oxygen, and look at the polarity of the bond in its resonance structure. So dimethyl sulfoxide. Whereas protic solvents such as water and alcohols would slow down the rate of SN2 reaction. So you should remember the order of reactivity toward SN2 reaction with respect to the type of alkyl halide you use, nucleophile, leaving group, and the solvent. N3-, by the way, is an acid ion. So acid will come from sodium or potassium acid, and that's another pseudo halide that's a potent nucleophile. So the structure of the acid ion. and there are several resonance structures. So sodium azide as a nucleophile, which has the order of reactivity similar to nitrile and bromide, or cyanide and bromide. So moving on to SN1 chemical reaction. SN1 occurs most readily at the tertiary centers and halides and tosylates. So since it proceeds via carbocation, tertiary and otherwise stabilized carbocations such as benzylic and allylic would react most rapidly. The solvent for SN1 reaction, in contrast to SN2, needs to be protic polar solvent, and you will recognize SN1 reaction by the solvent system, which typically will be alcohol mixed with water. And water increases the polarity of the solvent, whereas alcohol provides the organic component, since you cannot dissolve organic substrate in pure water. Mechanism follows a two-step pathway, with the rate determining step being dissociation of the leaving group. So step 1 is dissociation of the leaving group, leading to formation of the carbocation intermediate. Followed by addition of nucleophile to give us substituted product. So since the nucleophile does not partake in a rate determining step, therefore the nature of the nucleophile does not affect the rate of the reaction. And as long as nucleophile is present in appreciable concentration or amount, or it's even a co-solvent such as water, then the reaction rate will not be affected. So the rate of the reaction, therefore, will depend on the nature of the R-X, degree of substitution, and its general structure, on the type of the leaving group used, and on the solvent, since some types of solvents will promote or enhance stability of the carbocation better than others. Then we'll have to take a look at the three factors that will affect the rate: nature of the alkyl halide that undergoes the reaction, the type of solvent, and the type of leaving group. So SN1 reaction follows the same potential energy curve that is similar that you had seen for electrophilic reactions of alkenes. So the rate determining step is departure of the leaving group and formation of the carbocation. And to reach this transition state, transition state 1, that's the activation energy that we need. And the subsequent step, where nucleophile combines with the carbocation, is relatively fast. So as you recall, the Hammond postulate states that factors that stabilize the carbocation, our carbocation intermediate here, will be the same ones that will affect the relative stability of the transition state that leads to that carbocation. So we'll take a look at those factors as well. So formation of the carbocation is reversible. That's our rate K1 right here. Whereas trapping of the carbocation with nucleophile is irreversible. Once the sigma bond between the nucleophile and the carbocation forms, that product is then stable. So Let's take a look at the stereochemical outcome of SN1 reaction and see how it compares to the stereochemical outcome we discussed for the SN2 reaction when we saw inversion at the stereogenic center. Since carbocation is planar, trigonal planar at the carbon in question, so the three groups surrounding the carbocation have trigonal planar arrangement. So if you look at it from the top, and our carbocation will be surrounded by three groups. We'll have 60-degree angle looking at it from the top or from the bottom, with the unhybridized p orbital protruding above and below the plane of the carbocation. So here's a sideways view in a transition state. So in the intermediate. So we have a carbocation with the three groups in a flat arrangement, planar at the carbon, and the empty p orbital, the two lobes of the unhybridized p orbital protrude to the left and to the right. So since this is trigonal planar, the nucleophile can equally likely approach that empty p orbital from one side or from the other. And some theories describe how that the leaving group is still slightly associated with the carbocation in a transition state, leading to bias in the stereochemical outcome. But let's just focus on the most prevalent example where you will see inversion and retention occurring to the same extent, leading to loss of enantiopurity at the stereogenic of the product. So if you start with R enantiomer of a compound, if you have R configuration at the stereogenic center, then we will see that 50% of that R configuration will be retained. So here we have R stereochemical outcome, and the other 50% will be inverted to S, leading to racemic mixture and therefore loss of enantiopurity. So racemic mixture again of two enantiomers means that you have equal amount of each of the enantiomer, leading to a mixture that's not optically active. So let's take a look at the structure of alkyl halides and tosylates that undergo SN1 type of substitution. So we're looking at the compounds that, when dissociated, will lead to stable carbocation. So here we have a primary allylic carbocation, allylic meaning next door to the sp2 carbon. So we have primary allylic carbocation, which is stabilized by delocalization as we move the two electrons from the pi band back and forth, right? We have two resonance structures. Corresponding primary benzylic carbocation, benzylic means next door to the benzene ring, has more resonance structures since you can delocalize those two pi electrons across the framework of the benzene ring in addition to the sp2 hybridized carbon next door. So even though these are primary carbon atoms, we can still consider SN1 reaction pathway for those carbon atoms because they are delocalized. So the positive charge can be delocalized across the larger framework of the ion. Aliphatic or alkyl carbon atoms do not undergo SN1 reaction. So if you consider primary carbon atoms, they do not undergo SN1 reaction, and neither do methyl halides, which do not form, carbocations of that nature do not form in solution, but only in gas phase. They are too unstable. So let's focus on primary allylic and benzylic carbocations, as well as some secondary alkyl carbocations, and then tertiary alkyl halides. So the relative order of reactivity is tertiary will be much more reactive than secondary alkyl halide and the resultant carbocation, which is about just as reactive as the benzylic carbocation and allylic carbocation of the primary type. So primary allylic and benzylic are as reactive as the secondary alkyl carbocations. And then we will not consider methyl and primary. And needless to say, secondary allylic and benzylic will be even more reactive. So any allylic and benzylic carbocation would be more stable than the corresponding alkyl carbocation with the same degree of substitution. So for example, if you are asked to arrange several alkyl halides in the order of increasing reactivity toward SN1 reaction, let's take a look at the reacting centers. We have secondary benzylic alkyl halide. We have tertiary alkyl halide, primary alkyl halide, and primary allylic next door to the alkene. So according to the table above, tertiary alkyl will be most reactive, and secondary benzylic, since it's not on this table, but we can see that since primary benzylic has the same reactivity as the secondary alkyl, then we can deduce that secondary benzylic will be just as reactive as the tertiary alkyl carbocation. So B, tertiary, will be just as reactive as secondary benzylic A, which will be more reactive. We're comparing two primary carbons, one alkyl and the other allylic. Allylic carbocation would be delocalized, so D, whereas alkyl halide and its resultant carbocation would not undergo SN1 type reaction because the carbocation will be too unstable. If we compare the bond dissociation energies, bonds between primary carbon atoms and chloride, so in each case we have a primary carbon, we see that alkyl halide, that is primary, that bond is a little bit more stable, and depending on the structure, between 10 and 15 kilocals per mole, owing to resultant delocalization of the carbocations that are allylic and benzylic. So since allylic and benzylic alkyl halides have somewhat weaker bonds that are easier to break, they will lower the activation energy for the rate determining step in a SN2 reaction. Some types of halides and tosylates do not undergo SN2 mechanisms, and in addition to the primary ones that we already discussed. Now let's take a look at the leaving group, and we have the same table that we already saw for the SN2 mechanism. Since the leaving group dissociates in the rate determining step, then the order of reactivity of the leaving group will parallel that for the SN2 reaction. So again, those three circled groups, tosylate, iodide, and bromide, are best leaving groups for both SN1 and SN2 reactions. Strong bases, hydroxide, amide, and alkoxide, as well as fluoride, would not partake in an SN1 mechanism as they are very strong bases. They are not able to delocalize or stabilize their negative charge, and they will increase the activation energy for SN1 reaction. Nucleophiles in SN1 reaction, the nature or the amount of the nucleophile does not affect the rate. So here we have 2-methyl 2-propanol. And for the hydroxide leaving group and hydrogen, chloride, bromide, and iodide nucleophile, the reaction rate does not change. So as long as some nucleophile is present in an appreciable extent in some amount, and the nucleophile can even be co-solvent, that will not affect the rate of the chemical reaction. So we're just looking at the degree of substitution, the nature of the alkyl halide, the type of the leaving group, and the solvent. Solvent plays a critical role in SN1, just like it was the case in SN2 reaction. Here we're looking for opposite properties, whereas for SN2 we were looking for solvent that is polar but aprotic, solvent that couldn't donate hydrogen bonds. Opposite is true for SN1. We want solvent that is able to create a solvent cage around the carbocation. So since we have a full positive charge on the carbocation, protic solvent can stabilize it by solvation. So notice that the lone pair of electrons can stabilize the positive charge on the carbocation. Therefore, systems that include alcohol, such as ethanol or methanol, propanol, and so forth, plus small amount of water will best promote SN1 reaction. So here is the solvent reactivity, or solvents that best promote SN1 reaction. Notice that on one end of the spectrum we have pure alcohol with a relative rate of 1, increasing 100,000 times when we replace pure alcohol with pure water. So this is a theoretical value because obviously you will not be able to dissolve most of the organic substrates in water, so you should not select water as the best solvent for SN1 reaction. You need organic component as well. So realistically, best solvent system for SN1 reaction will be alcohol mixed with water. For example, system that is 80% water and 20% ethanol would be better than system that is 70% water and 30% ethanol. So to summarize the two mechanisms that we had overviewed here, SN1 and SN2, what you want to do is to look at the nature of the substitution of the alkyl halide first and designate it. Describe what it is. So in the example here, reaction A, I will look at the nature of the R-X, which in my case is secondary alkyl tosylate. So secondaries, the gray area, can go via SN1 or SN2. So I need to look at the other reaction conditions. First, I will look above the arrow. And first of all, you need to have a nucleophile, because if you have a base, you will probably have elimination reaction, which we'll talk about next. But since I have nucleophile, then I know that this is nucleophilic substitution, and I still do not know which mechanism will prevail here, SN1 or SN2. So I look below the arrow and take a look at the solvent. I have DMSO, dimethyl sulfoxide, which is one of those 4 polar aprotic solvents that best promote SN2 reaction. So when you see DMSO, acetonitrile, when you see DMF, and hexamethylphosphoramide, HMPA, then you know you have SN2 reaction. So since I have SN2 reaction conditions, and I see that I have a stereogenic center, then my product will have the opposite configuration of the stereogenic center, because during the nucleophilic attack and dissociation of the leaving group, the stereogenic center is inverted. So my mechanism, which is one-step mechanism, SN2 reaction, my nucleophile cyanide ion with a full negative charge on carbon, so sodium cyanide, will attack the carbon atom from the backside. Tosylate will be expelled, leading to hydrogen being pushed toward the back, and my nucleophile coming out in the front. So predicting the product is easy once you find and recognize the pattern, and then recognize the reaction conditions. Example below, I have the same substrate, again, secondary alkyl tosylate, R-X. I have the same nucleophile, sodium cyanide, but my solvent is different. I have polar protic solvent system consisting of 80% ethanol and water as co-solvent. So I'll recognize this as SN1 reaction mechanism, which proceeds through via 2 steps. Step 1 is the rate determining step, dissociation of the leaving group. And since my carbocation is trigonal planar, I lose the absolute configuration at the stereogenic center. So my carbocation is trigonal planar, so I cannot talk about configuration R or S in the intermediate since I don't have 4 groups attached to the carbon in question. And then my cyanide nucleophile can approach my carbocation equally likely from the top or from the bottom, leading to racemic product. So in the product, I will just draw racemic structure without indicating R or S configuration at the stereogenic center.